Right, so in question 1676, we have a bird flying towards a stationary bird watcher. And it's tweeting along and emitting a certain frequency as it does so. So that frequency that it's putting out is 1,250 hertz, but that's not what the bird watcher hears. This bird watcher, which is watching this bird approach him, is actually hearing a frequency that's a bit higher than that, 1,290. So this sounds to me like a Doppler effect question, because what we have here is the effect where we have an observer listening to a source of sound which is moving and hearing a frequency which is actually different to what the source is emitting. So it's kind of like if we're standing next to a road and a car comes along honking its horn, then when that honking its horn car is coming towards us, we hear a higher frequency for the honk, so we hear a higher pitch than when it's going away from us. So we hear the frequency, so the pitch go from something that's higher down to something that's lower as that car passes. And the Doppler effect, of course, is expressed by this little formula here, which says that the frequency of sound which is perceived by an observer is equal to the frequency of sound which is emitted by a source of that sound, but multiplied by a factor that is this. It's the speed of sound plus or minus the speed of the observer divided by the speed of sound plus or minus the speed of the source. So if I just label what this is speed of sound. So presumably the speed of sound is in air in this case. This is the speed of observer. And this thing here is the speed of the source. In this case, a bird. And this formula here, courtesy of these plus or minus signs, is actually 4 equations rolled into one. And we need to pick these minus signs by thinking about what situation we have. But we can make this a little bit simpler. And since the bird watcher is just stationary, this VD, so this speed of the observer, is just equal to 0. And in that case, the formula becomes a little bit simpler. So in fact, if we have a stationary observer, then there's only one plus or minus sign that we need to concentrate on. Now, because the perceived frequency is higher than the frequency which the bird is emitting, we know that this factor here has got to be greater than 1. So practically what that means is that this denominator here has to be less than the numerator. And the only way we're going to achieve that is if we choose the minus sign. If we chose the plus sign, then the denominator would be greater than the numerator and the overall fraction would be less than 1. So here we know that because the bird is coming towards us and the bird watcher hears a higher frequency, or perceives a higher frequency, we need to choose the minus sign. So here we choose minus sign. So choose minus sign. Since the perceived frequency, which I call f prime, is greater than the actual frequency, which I've called f. So the formula that we really want to be using is this one here. And pretty much what the question wants us to do is to figure out what the speed of the bird is, given that f prime, so the perceived frequency, is 1,290 hertz, and the actual frequency being emitted is 1,250 hertz. So armed with the knowledge of those two, we just want to figure out what the speed of the bird is as a percentage of the speed of sound. So first of all, let's figure out what the speed of the bird is as a fraction of the speed of sound, and then from that we can figure out what the percentage is. So what we're really after here is VB divided by V. So to get that, let's first of all divide both sides by f. So if we did that, we would end up with perceived frequency divided by actual frequency is just going to be the speed of sound divided by the speed of sound minus VB. And what we can do to this is, because we just have one fraction equal to another fraction, we can just flip both sides of this. We can turn both sides upside down, because if the set of fractions up one way is true, then if we turn them upside down, then that's also got to be true. So this tells us that the actual frequency, so f divided by f prime, is going to be equal to v minus vb divided by v. And this we can simplify out, because let's just break up this fraction and write it into two bits, v divided by v and vb divided by v. And now we see that because v divided by v is just equal to 1, this thing is just 1 minus vb divided by v, and this is the thing that we're after. So if we just solve this equation for vb on v now, what we're going to end up with is that that's equal to 1 minus the ratio of those two frequencies. And that, if I just shove this into the calculator, it's going to be equal to 1 minus... Sorry, I've just made a mistake here. So I went from here to here, but I just copied it out wrong. Sorry about that. So this should be f divided by f prime. Assuming you can see that, of course. So what I calculate is 1 minus 1,250 divided by 1,290, which comes out to 0.031. So VB divided by V is 0.31. To convert that to a percentage, we just need to multiply by 100, which gives us 3.1. So VB is 3.1% of V, i.e. speed of sound.